I wanted to have a go today at explaining hexadecimal, so what it is, what it's for and how to use it. So hexadecimal of course is base 16 and it comes up a lot in computing and computer science. But what's the reason that we use hexadecimal? Well, first of all, in order to understand what hexadecimal is, let's understand what decimal is. So this is, the kind of numbering system that we're most familiar with as humans. So if you can remember at school, looking at these tables describing what decimal numbers mean. So we've got ones, sometimes they wrote that as U for units. We've got tens, and we've got H for hundreds, like so. So when we say 326, what we're actually saying is we've got 3 times 100 plus 2 times 10 plus 1 times 6. So in decimal, each column that we look at is 10 times more than the one below. So you start with 0 in this position and you can count up to 9, but once you get to 9, then you need to add 1 to the next column, and this one goes back to 0. So that gives us some idea about what we mean by a base, a number base, a numbering system. So if we look at hexadecimal, in hexadecimal, the system says that every column is 16 times more than the previous one. So we've got the ones, and we've got 16s, and we've got 256s, and then 4096. So each is 16 times the previous one. So if we had the number 22, for example, then what we're saying there is we've got 2 times 16 plus 2 times 1. So 2 times 16 is 32, plus 2 is 34. So in decimal, this would be 34. But in hexadecimal, we call it 22. And so there are a number of different ways of denoting hexadecimal. So one way that used to be used a lot is to just use an H, so 22H or big H, basically represented the same as 34 in decimal. Or a very common convention that's used now is to say 0x22. So 0x22 is 34 in decimal. So this notation 0x, I think, came from the language C, but it's now very, very commonplace, and you see it in certainly in a lot of languages that derive from C, like Java, JavaScript, C#, even from Python, and so this is a very common notation. So why do we do these jumps in 16s in hexadecimal? The main reason for that is that the hexadecimal digits are very closely related with the binary bits underneath, and computers operate in binary. So for computers we want to be close to binary, but for humans we want to be close to decimal. So hexadecimal is kind of a halfway house. It allows us as humans to understand numbers better, while at the same time being convenient for computers. So if we look at binary for a moment, so looking again at this kind of number chart approach, what happens in binary is we've got each column is 2 times the previous column, like so. So we've got 1s, 2s, 4s and 8s. So if, for example, we had 0, 1, 1, 0, because remember in binary we can only have the digits 0 and 1. So if we had this sequence 0, 1, 1, 0, then like the other examples, what that means is we've got 4 times 1 plus 2 times 1 plus 0. So that means we've got 4 plus 2, and that's equal to 6. So 0, 1, 1, 0 is equal to 6. Now there's a very close relationship between binary and hexadecimal. So if we look at that 0, 1, 1, 0, in fact in hexadecimal this is also known as 6. And if we have a look at, if we list out some of the other digits, you can see the relationship between the binary and the hexadecimal. So you'll notice that we need 4 digits of binary to add up to 1 digit of hexadecimal, and this is quite useful, as we'll see in a moment, for decoding binary numbers or switching between binary and hexadecimal. So here we have the binary sequence. So we've got starting with 0, we clock the 1s, then we move on to 1, 0. When we add 1 to 0, 1, because we can only have 0s or 1s in these columns. Once we get to 0, 1 and we have to add another 1, what we need to do is carry the 1 to the next column. So you get 0, 1 followed by 1, 0, then we've got 1, 1, and now that all of the 2's and the 1's place is are taken up, when we add 1 we have to go to 1, 0, 0. So in hexadecimal you've got 0, 1, 2, 3, 4, 5, like that. So in each case exactly 4 bits of binary corresponds to 1 digit of hexadecimal, and this is something that makes it really convenient to change between hexadecimal, between binary and hexadecimal. So if, for example, we had the number 66, so hexadecimal 66, what we can do is we can look at each digit in turn, and each digit has to map to 4 bits of binary. So in binary this would be 6, which would be 0110, followed by another 6, 0110. So just by looking at each digit at a time we can generate a binary number. And similarly, if we had a binary number like so, we could translate it into hexadecimal just by moving from right to left and breaking up the groups of 4 bits. So if we put lines in there to indicate where the 4 bits are, now we just need to look up 001, which is obviously the hexadecimal digit 1, and 0100, which is the equivalent hexadecimal would be 4, and we can see that this is 41, so this is the hexadecimal number 41. So it's really quite easy to translate between hexadecimal and binary, which is what makes hexadecimal so useful. Now one thing that you might have noticed is because you've got four digits here, we can actually go above 9 in 4 digits, which means that we actually run out of symbols. So if we do that, so we got 0111 would give us 7, 1000 is 8, so now we've got to 9, but we've got a few more sequences that we need to represent. So 1010, 1011, 1100, 1101, 1110, 1111. So we now have got 1, 2, 3, 4, 5, 6 numbers that we have to represent in hexadecimal, but we don't have any digits left because we've gone from 0 to 9. And this is where hexadecimal switches to the alphabet instead. So we start representing them as A, B, and so on. So we've got A, B, C, D, E, F. So similarly, as looking at that example earlier, if we had the example, we've got binary 1110 followed by 0010. In order to code that as hexadecimal, once again we go from right to left, splitting it into groups of 4, like so. 1110, if we look it up in the table here, is E. And 0010 would give us 2. So this binary number is E2, or 0xE2, or E2H if you're using that convention. So it looks a bit odd to the human eye at first, having digits and numbers inside the same number, but it gives us quite a lot of flexibility, because now we have in 2 digits we have the numbers 0001 all the way to FF, and in decimal this gives us up to 255, so we can count up to 255 just by using 2 digits. So it's quite space efficient, and in fact 2 digits is the same as a byte, and so in computer memory each location that contains a byte can contain a number 0 to 255. So back when I started using computers, we used to have what were called 8-bit computers, and 8-bit basically means that the memory is 8 bits wide. So we might have, in binary, we've got 8 bits side by side, which can go from all zeros to all ones. And now looking at hexadecimal, we know now that we can say that 00 hexadecimal is the same as all those zeros in binary, and we can say that all the ones can be represented by FF. So each 8-bit location could contain 00 to FF. Now in modern computers, the word size in computers is often bigger, so in a 16-bit computer you've got, now there's the 8 bits and there's another 8 bits by the side of it, so each data word now is 16 bits long. And looking at the world of hexadecimal again, we can now, if we split this into 4 using our trick, we can see that 0000 hex is the same value. So once again, in 4 digits or in 2 bytes, we've represented a very large range of numbers. So in a 16-bit system you can have all the ones in each memory location like that, which would give us the FF. And if you work it out, this gives a maximum number range of, in decimal, of 0 to 65535. So all ones, or FFFF, is 65535. So if you've ever seen that magic number, you know this is the biggest number that you can represent in 16 bits. And similarly, you know, when you go to a 32-bit system, 32 bits, I won't write out all the binary, but you can imagine you've got 32 ones or zeros, and in hexadecimal that could be, the maximum number would then be FF followed by FF. And that means that the biggest number you can represent in 32 bits is this rather large number, 2,147,483,647. So that's the biggest number that you can represent in 32 bits. And similarly, when you get to 64 bits, and you now have not just the 4 hexadecimal digits, 4 hexadecimal bytes rather, 1, 2, 3, 4. In a 64-bit system, you would now have 8 hexadecimal bytes. So you can imagine that the number is much bigger than that, because now you can count up to 2 billion in just the 4 digits, and then you can roll over into the next column and have 1. So you've got 2 billion variations, and then another 2 billion variations in front of it. So that's a very, very large number. Just as an aside, in computing, some languages, some systems used to use a base called octal, and octal is base 8. So in base 2 we can only count from 0 to 1, so binary. In decimal we can count from 0 to 9. In hexadecimal we can count from 0 to F, of course, so we've got 16 variations, and octal fits in there low down here, and we can count from 0 to 7. So in octal you only see the digits 0 to 7, so 3, 4, 3 for example is a valid octal number, but you couldn't have 3, 4, 8 because 8 would carry a 1, it would become a 5 in this column. So computer scientists used to use octal, and if you ever encounter octal, there's a similar trick as with hexadecimal. What we can do is we can look at the individual digits, and this time each digit only represents 3 bits. So we would then say that this digit here could be represented as 0, 1, 1. So that's 1, 2 plus 1, 1. That gives us 3. So 3 digit is 0, 1, 1 in binary. A 4 is 1, 0, 0 in binary. And a 3, again, 0, 1, 1 in binary. So then, if we then converted that into hexadecimal, so let's split them into groups of 4, and now we can work from right to left and code them again. So 0, 1, 1 is 3, and 1, 1, 1, 0 is E. So there we go, we've got 0xE3 is the same as 343 in octal. So that's a quick summary of hexadecimal, the meaning of hexadecimal, a little diversion of into octal, and I hope that's been useful for you in understanding the relationship between binary, hexadecimal and decimal.